Okay, guys, so let me just stress a few things. So first of all, this manipulation that we did with this integral over d4x giving us this delta function, this is a very common thing. You're going to see this coming up many, many times. So really you need to learn this formula that the integral d4x e to the I x dot p3 minus p1 is 2 pi to the 4 times a four-dimensional delta, which sets p3 equal to p1. This is extremely important. And then what did we do? We integrated over d3p using the delta function. So we integrated over d3p, and notice there's a 1 over 2 pi to the 4, and that cancelled with our 2 pi to the 4 and the delta function. That will also always happen, okay? So that 2 pi to the 4 comes with each delta, and when we integrate over it, d4p has 1 over 2 pi to the 4. And that was our final result for this diagram. Now, one of the things that I wanted to stress, so there's something rather interesting going on here. So let's look at this vertex, okay? So there's the vertex, and I only want to look at the momenta that are flowing around this vertex. So let's color code things a little bit. So we've got the blue lines. So here there's a blue line, here there's a blue line, we've got a green line, and we've got a red line. Now, this red line over here, this corresponded to a momentum P1 flowing into the vertex. The green line corresponded to a momentum P3 flowing out of the vertex. With the blue line, you can see we've got P2 flowing out this way, and then the line turns around and comes back on itself. So we've got a P2 flowing in here. Now, what should the conservation of momentum say? It should say the momentum flowing into the vertex must be equal to the momentum flowing out of the vertex. So P1 plus P2 has to be equal to P2 plus P3. But we can cancel the P2s on both sides, so we learn that P1 must be equal to P3. And this is all of the components of momentum. So it's all four components. So what we see is the integral over x, which gave us this four-dimensional delta function, setting all of the components of P3 equal to the components of P1, it was actually implementing the conservation of energy momentum at this vertex. And that was done by the integral over x, okay? Again, this is a very general statement. You'll see this again and again. Very good. Okay, let's just write down one more example, but I think that you really do have the idea now, but let's just write down one more. So let's study this diagram over here. Okay, so I'll just copy that, duplicate, and let's carry it down here to the bottom. Very good. So let's now write down what we get from this diagram. So first of all, there's two vertices. So we will have a minus ig times by the 4 factorial, and it'll be squared because we've got two vertices. And we need to integrate now over the position of the first vertex, that means d4x, and over the position of the second vertex, and that means d4y. And now we need to start putting in the rules for the lines. So we've got one propagator going from x1 to x. So we'll have g x1 to x. And then there are three propagators going from x to y, okay? Here's one. Here is one. And here is one. So there's actually three propagators going from x to y. So if we put those in, we've got a g of x comma y cubed, and then we've got a g of y comma x2. And then we need to take into account any symmetry factors or anything like that. Well, the three lines going from x to y, they've got the same start points and the same end points. So we need a 1 over 3 factorial, and that's from the equivalent lines. There are no closed lines. Those two vertices are not equivalent. You know, the one vertex is distinguished because it connects to x1. The other vertex is distinguished because it connects to x2. And there's no equivalent diagrams. We just have one diagram. Good. So now let me make a suggestion to you. You could plug in the expressions for g, okay? You could plug those in. And then you could do the integral d4x and the integral d4y. What you should find in both cases, all that you need to do these integrals is this formula. So you really need to commit this to memory. E to the I x dot k is equal to, there's a 2 pi to the 4, and then there's a 4-dimensional delta that will set this k, whatever multiplies x, to 0, okay? And this is what set P3 is equal to P1 for us previously, okay? So this is all you should need to do both the integral over x and the integral over y. And once you've done that, you should then be able to verify that the integral over x gives you a delta function which conserves momentum at the vertex at x, and the integral over y gives you a delta function which conserves momentum at the vertex labeled y. And then you would be left with an integral over momenta. And we're going to be discussing how to do those integral over the momenta in detail a little later in the course.